Okay, let's go ahead and get started with today's lecture. What we're going to do is cover the homework. So the homework that I gave you was actually pretty simple. I know that's almost arrogant, condescending for me to say, but I mean it for what it is, and you'll see once we go through the program. Basically, what I wanted you to do is just an extension of calculating the area under a curve. I just want you to calculate the volume under a surface. So the surface that I gave you is just y equals x squared plus y squared. So it's basically just a revolved parabola. So just take a parabola revolving around the z-axis, and that's what the function is. From the limits a1, a2, b1, b2, and basically we have square or rectangular limits. So what I want you to do is just write a program where you input these limits, and then n, where n squared is the number of boxes. So if you type in like n is equal to 10, you'll actually calculate a 10 times 10 grid. Okay. Um, Otherwise, if n was the total number of boxes, then you'd have to take the square root of n, closest integer to that. So it's just easier to say n and say, so if you want 100 boxes, do n of 10. Whereas in under area, n was actually equal to the number of intervals. Okay, and then I gave you some of these links just to kind of give you some insights into what the problem actually is. So I'm just going to go through the code. I'm going to provide this spreadsheet. I'll post it in Moodle. Just I did this in Mathematica just so you can kind of see what these surfaces look like, and also give you a couple examples over here with the limits. So when you plug your numbers in, you can see if it's actually right. Okay. If I'm not mistaken, the reason why I have this Control C is if I go into Wolfram Alpha, I think that's how you actually do a double interval. There's several ways to do it, but I think if you just actually type in the word double integral, the equation, and then from x, yeah, it does. So it's pretty smart. Okay. So that's how you would actually say do it in Mathematica. All right. All right. So let's go up here under our code, and I'm going to run through this, and it's really simple. Okay. So I come up here and I declare a bunch of variables that I'm going to be using. All right, so you may say, well, okay, that's great, but how did you know to declare these variables? Well, first of all, remember you don't actually have to declare a variable. You can actually, and I do it all the time, I declare variables as I need them. So as I'm writing my code, be like, oh, I need another variable. Well, let me go up there and declare it. And declaring variables it's just strictly for the purpose of basically if you misspell one in the code, it tells you. Um, and if you come up here and you write option explicit, okay, what option explicit means is that if the variable's not declared, it doesn't get used. Okay, so the only reason why you use option explicit is if you misspell a variable or if you change the code or something, and you don't have that variable defined, when you go to debug it, instead of you getting some strange answer and you try to trace that down, it'll just simply say, variable not defined, okay? And this is actually really useful because I can't tell you how many hours in my life I've spent trying to debug a program only to find that, like, I spelled interval interval, and then somewhere down here I happened to leave out an R, and then that variable that just said, oh, well, this is a new variable, we'll just let it be 0. And you trace it down and you're not getting an error message, you're actually getting an answer. So that's why you may want to do that. So these are the variables I declare. Like I said, you look at it and say, yeah, but how did you know to declare these? Well, because as I wrote the program, I kind of declared them. So it's not something you even have to worry about in the beginning unless you kind of know where you're going. Um, this is super simple. We all get this. This is just declaring the bounds for the limits. So XLB is X lower bound, XUB is X upper bound, YLB, YUB, and then the interval is just how many n, you call it interval n. I just say number of divisions. Okay? Got that? Super simple. All right, determine the x and y width of the rectangle projected on the xy axis. This is real simple. The width of the x in the x direction is just the upper bound minus the lower bound divided by the interval. The y is the upper bound minus the lower bound divided by the interval. So the reason why we have two different values, obviously, is because our x and y can be different. We're calculating the area of a rectangle projected onto the surface, not a square. If it was a square, you'd only need one variable. Okay, half width. This is pretty simple to understand. All I'm trying to do, what I will use this for, is just to find the middle of each interval. So if I could use calculating the midpoint, I just need to know the midpoint of each interval. So that's all there is to that. All right. Any questions so far? Nope. All right. Temp volume and volume, I'm just initializing them at 0. Temp volume is the volume that I use to add on to my total volume. It's kind of a placeholder. Okay, so the first thing I do is I say, well, let me calculate this line of code right here. And the reason why I have this each time is basically I reinitialize it to 0 before I do a different estimate. So I'm going to say, let me calculate the volume using the left estimate, which is basically the lower value, the lower xy. I could say lower estimate. I called it left estimate because that's what I called it when I calculated surface. But I could just replace the left and say lower estimate. So it's the lower, like left-hand bottom corner of each rectangular solid. That's all that is. Okay, so then that's real simple to do. I just do a nested for next loop. So I say for j equal interval minus 1, for j equals 0 to interval minus 1, for I equals 0 to interval minus 1. So the reason why I start at 0 is, think about it, I'm literally, let's suppose my lower bound was at the origin, and I'm going to start out at that lowest left-hand bottom corner of my rectangles, okay? So I'm going to start out at 0 because when I multiply this j and this I times the width here, the answer I'm going to get is 0 because I multiplied it times 0. So these are really easy to understand. My first x value is just going to be my x value that I start out. That's going to be the value that I define as x. It's just going to be my x lower bound, whatever I plug into that, plus j, which starts out at 0, times the width of x. So this quantity right here is 0 added to my lower bound, so my first x value is going to be 0. Or, I'm sorry, it's going to be my x lower bound. The same is true with y. Okay? So now I just say temp volume is equal to volume. Okay? Both of them start out equal to 0. And then I say volume is going to be equal to the temp volume, which is my placeholder, which starts out as 0, times the volume of that rectangular box, which is length times width times height. Where does height come from? It's a subroutine down here that I define as x squared plus y squared. So I just plug in my x and y value. That tells me my height. And this is my volume. Count equals count plus 1. To be honest with you, I don't think I even need that. I think I was looking to do I'm going to comment it out just to make sure. But I think what I was doing when I wrote this code is I was looking at doing a do while loop instead of a for next loop. But then I realized, let me just do a for next loop and we'll declare n. With the do while loop, you would have to calculate multiple times. So you would have to let n be a value, and then maybe you double the value of n on the next time, and you compare the answers, and you would declare an epsilon. And so in a sense, it's like finding what n needs to be such that the value would be less than epsilon, like we did when we were calculating like Newton's method or something like that. So this was really just a mistake of me leaving it in. All right. Then I just loop next I, next j, and that's all there is to it. That's all there is for calculating the left estimate. Calculating the right estimate, the exact same thing. Um, I accidentally left this in, but I can delete that one out too. Comment this. All right, so except the only difference is here I started out 0 to interval -1. For the right, I start out 1 to interval. And that's simply just because I'm going to be calculating my right. Instead of my lower left-hand corner, I will be using my upper right-hand corner, right? So instead of starting at 0, I start at 1. So when I do this, calculate this first value of x, it's going to be my lower bound plus 1 times my width, which moves me up to my right side upper corner of the box. And I do the exact same thing. All right. Midpoint's a little more complicated, but not really. It's just like using the left estimate. The only thing I do is I just add a half width. So imagine that I'm in my, I guess I could draw something instead of just talking about it. So when I say this is going to be my left estimate, it's this point here. This I call my right estimate, but I could just call it also my upper. Okay. The mid is going to be right here. So this is where I get this half width value, the one that I called half width x, and then this value right here is my half width y. Okay. So all I'm doing is just using my left estimate, and then I'm just adding the half width. And the half width that's why I went up here and calculated my half width as being my width divided by 2. So this just literally takes me to the middle of the box, right smack dab in the middle. And then that's what I use for my XY values, and that's calculates the height at the middle. Okay? And then I do one more, and the one I do here is I use what I call a diamond shaped box. It's called a, I looked it up the other day. It took me a long time to figure out what it's called. It's called I think a half cube or half prism, and essentially this is what it looks like. There you go. Kind of like that building in Chicago. So what you do is you just take a rectangular box and you cut it like a compound miter cut. You just cut it at an angle from diagonal to diagonal. Okay? And if you think about it, that's what you're really doing here. If you were to calculate the volume of each one of these like facets, a rectangle is a good approximation, but if you want a better approximation, simply this is like a three-dimensional trapezoid is all it is. Okay? So you have to calculate the volume of that, but it's really easy to do. So if you have, and there's no way I'm going to be able to draw this to look halfway decent, just because I'm not a good artist. Let's see, maybe I'll do it like this. So I suppose I've got a box that looks like this. And I want to calculate kind of the trapezoidal volume. What I do is I just cut it in half. Let me say right here. Just cut the thing in half. So like I pick a point, say right here, and then right here, and then I don't know, just kind of cut it. Right. And when I do that, it literally looks like this. So then how do I calculate the volume of this? Well, it's really the same formula as a trapezoid, but what I end up doing is I have to know my min value and my max value. Those are the only two that I'm interested in. So with a trapezoid, I only have 2 points. So if you think about having a trapezoid, it looks like this. Okay, and so then I have the B1, B2, and so then what I do is take a copy of this and turn it upside down, and this becomes B1 and B2. So the area of the trapezoid is the height times B1 plus B2 over 2, right? Everybody get that? For this half cube, you do the exact same thing, but instead of just having a B1 and B2, you have basically a B1, a B2, a B3, and a B4. Okay? So let's see if I can paste this in and try to make a little sense of it. So in this particular case, let's suppose that this is like B1 is this height, and then we'll say this one is B2, this height, B3 is this height, and B4 is that height. The way I will calculate the volume is I'll just need to know the value of B1 and B4, okay? Because I'm cutting across from the long end to the short end. So I don't even need to know these. But it could have been that B2 was smaller than B1. It would be cut in another way. So the easiest way to do this is you just take the min value of B1, B2, B3, and B4, and then you take the max value of B1, B2, B3, and B4, okay? And that's how you determine, like, say, your B1 and B2 analogy in a trapezoid. Does that make sense? So you have to, it's really easy. You just have to think about how you would make this. And the easiest way to make this is just to take a rectangular box and to cut it at the diagonal. Okay? I mean, that's, if you really wanted to make one of them, that's all you would do. Just imagine you have this long rectangular box and you want to make one of these half cubes. I mean, if you cut the sucker right in half, all the B's are going to be the same. If you cut it, say, at a miter, 2 of the B's will be the same. If you cut it at a compound, 2 B's will be the same also. But if you do like a compound to miter cut, so if you've ever seen one of these big compound miter saws, you can either, cut a miter, or you can cut what's called a bevel, okay? Or you can do both. And it turns out that's really complicated, because I know I've had to deal with it before in my life, trying to figure it out. And then I figured out what carpenters do is they just literally hold like the piece of trim at the angle that's going to be put up at, and then they just do like a miter cut, and it takes care of it. And so you can learn a lot from working from somebody that actually knows how to do that. But I remember years ago me going in and I was going to actually figure out what those angles were, and I realized, wow, that's really, really complicated to do. But what you do is if you want to say I hold this keyboard up and I want to cut it to where it'll fit in a corner, all I do is just hold the keyboard up at an angle, and then I just cut on a 45, and it automatically cuts what the angle needs to be. But now when I lay it flat, you look at it, it's like, man, that's a complicated angle. But it's actually, if you try to figure it out, it is complicated. But from a practical point of view, it's really simple to do. So is it clear why I take the min and max of these heights? Okay. And so then when I do that, basically this is what I do. I calculate 4 points. So instead of just x, y, I calculate x0, y0, x1, y1. Okay? And I calculate the low points. I calculate the low x's and the high x's. The low x's, the low y's, the high x, and the high y. So I basically calculate the 4 points. And then I just let temp volume equal volume, which is kind of my placeholder. Then I calculate the height of those 4 points. Okay? So all I'm doing is if I grab, say, one of these right here, all right, all I'm doing is, let me just pick, say, a rectangle. I'm calculating the height of this point, the height of this point, the height of this point, and the height of this point. All right, because I got 4 points, and I just picked a random rectangle or facet inside of here. So I know the xy of each one of these 4 points, and then to calculate the z, it's really simple. I just plug in the xy into the function that I use. So now I know the height of all of these, and I know the xy of all of these. And so then I just calculate the min of those 4 heights and the max of those 4 heights. And then the volume is just the width times the height, so it's the area of the base, times max z plus min z divided by 2. Okay? Which is, like I just showed you, the area of a trapezoid is this, so the volume of this rectangle, or this half cube, will just be L times W, L times W times just what I have, min Z plus max Z divided by 2. And that's what the area of this is. Is that clear? I mean, it really is simple. It's just like having a 3-dimensional trapezoid in a way. All right. And then you just keep your volume. And like I said, I don't even need this count guy. And then I just call it trap volume instead of left, right, or mid volume. And then here I just report it. That's all there is to it. So if I come up here and I do one of these, shouldn't have done that. I didn't define x and y. X comes y. I was trying to make a point. I made a point all right. Yep. Well, I don't need count, but I'm afraid to delete it. You ever do that?
Yes.
Yeah. I know it's not doing anything, and I will delete it. But I don't want to delete it and then hit run and it not work. XO. Anyway, I'm going to get rid of the option explicit because I know the code will work. Okay. Told you you didn't need it. All right, lower bound. So let's do this example here. We're going to plug in a value of 0, 5, 0, 5, and then we'll say n number of divisions. Let's just say 10. And here are the answers. If I use my left estimate, I get 356, right 481. Mid is 415.6. So you see I'm getting pretty close. Using the trapezoidal estimate, it's 418.75, which is actually closer than the 415. But if I increase this to say 100, now I'm getting really close. So my actual answer is like 416.667. I'm getting, for my trap volume, 416.68. So I'm only off like 0.02 at this point. Okay? Does that make sense? Any questions? It was simple, wasn't it?
It is.
Okay.
It's like what I said yesterday. Whenever we're in here, it's like it makes so much sense. And we leave.
Right. Yeah, I get it. I mean, it looks complicated because I'm doing four estimates, but if you just pick any one of them, it's like it's only, I mean, the actual code is like 1, 2, 3, 4, 5, 6, 7, 8. I'm not going to count reporting the value or initializing these as lines of codes. The actual work is being done in 8 lines of code. I mean, you can say, well, you had to input the values. Okay, I'm sorry, I had to input the values. But I'm saying the engine of this double integral code is only 8 lines of code, which to me I find really kind of fascinating. That of the infinite number of three-dimensional surfaces out there, that 8 lines of code will calculate the volume of all of those surfaces, under all those surfaces. Now you could argue, yeah, but you've got this one and it has a discontinuity, or it does, okay, yeah, all right, fine, I'll give you that. That every now and then you get a strange function and it just blows up on you. But I'm talking for the bulk of the continuous functions. Well, continuous really defines it. There's an infinite number of those. That if you want to calculate the volume under that surface, it only takes 8 lines of code to do that. And then work. And that's what I was saying. If computers, which would be an impossibility, but were out before they started working on calculus, a lot of people would have just bypassed it. It's kind of like what we do now with calculators. Okay, you have to learn it because you're in school, but how many people actually do long division or multiplication or even addition of big problems in their head anymore, or pencil and paper? I mean, you're down to having nothing before you do it. Well, the same is actually true with calculus and numerical analysis. That calculating integrals is really just 8 lines of code, and it gives you answers that really are more useful to us as human beings because it's numbers, which is what we're usually interested in. Like how much does it weigh, or how much paint do we need to cover it? All right, is that clear? Okay, now I'm going to show you how to do one three-dimensional surface area. So just like I showed you arc length, remember that? I'm going to show you how to do it. So calculating the surface area of a function is actually a little complicated because you have to plug into this formula right here where you take the double integral of the partial derivative with respect to x plus the partial derivative with respect to y, square them both, add them together, and then add them to 1. So what ends up happening is a lot of functions that you want to calculate you can't do in closed form because you get these complicated functions that are under a radical. And if you recall how to integrate, if you have something under a radical, you have to plug into some formula, and sometimes it's just not at the form where we actually know how to do it in closed form. All right, so so yeah, actually calculating the surface area probably more often than not, if you just pick a random function, you're not actually going to be able to calculate that in a closed form. So you'll have to use some type of approximation. So like for instance, this is how you would calculate the for the function of this parabola I was talking about. If you wanted to calculate it over the bounds of -2 to 2, this is what you would actually have to end up doing. you actually have to take the partial, the derivative with respect to x and y, and plug it in and do all that sort of stuff. But I'm going to teach you how to calculate it using.
Is full conditions numerical or are they symbolic or both?
It will always, unless you type in n for n, like integrate or something, or n derivative, it will always try to do it in symbolic form. And then a lot of times it will just crank out like pages of stuff that you don't understand. I guess where they've done so much work on it. Uh, and then it'll say, okay, and the approximate answer is this. Okay. But like if you type in this, say, n integrate, what it does is use numerical analysis.
Mm-hmm.
So that n tells it, okay, skip trying to figure it out symbolically, just give me a decimal answer. So that's what the n usually does in front of a function. Like if you type in n solve, for instance, if you type in solve, it'll try to solve it in symbolic form. If you type in n solve, it'll use something like Newton's method. Okay, so what you're going to do is you're going to calculate the area of each one of these little squares. Well, they're not really squares, they're quadrilaterals, okay? So how do you calculate the area of a quadrilateral? Well, it depends. I mean, is it a parallelogram? Is it a square? Is it a rhombus? Is it a trapezoid? Well, here's what you can do, and this is what I did, is I just went in and said, all right, well, instead of trying to figure out the area of a quadrilateral, let me just go in and break each one of these up into triangles. And this is actually how, like in graphics art programs, this is how they do this. They're called I forget what they're called, facets, I guess. But they use triangles. They break everything up into triangles, and here's why. Because there was this famous guy, Heron, Heron's formula. And I can't remember when he lived. Who would know this? Nobody would know it. That's who. Well, he was hero of Alexandria, so, you know, old. CE 60, so right around old, yeah, roughly 2,000 years ago. He came up with a formula to calculate the area of any given triangle. Any given triangle. And you don't have to know the angles or anything. All you have to know are the sides. And the way you calculate it is if you know side A, B, and C, you simply add up the sides, A, B, and C, divide by 2. This gives you what's called a semi-perimeter of the triangle. So if you were to go around the triangle, calculate the perimeter of the triangle, this is basically that perimeter divided by 2. And you plug into this formula, the square root of S times the quantity S minus A times the quantity S minus B times the quantity S minus C. And it'll calculate the area of any triangle. So we're going to use that to our advantage because we can calculate A, B, and C, even though they're in 3 dimensions. It's easy to do. Okay. So what we're going to do is real simple. Here's our inputs. Here's our interval. Okay? Here's our with x, with y. We've already covered this. You guys got that? We're going to call instead of volume, it'll be surface area. We're going to initialize that to be equal to 0. And then we start our nested for next loop. All right? And it's actually really easy to do. So the first thing we're going to do is we are going to calculate the x and y values of all 4 of those coordinates, which we already did in calculating the volume. It's just we want to know the x, y coordinates of each one of those little rectangles that are projected upward. Right? Simple enough. Then we're going to calculate the z value, or the height of each one of those. We've already done that, right? Got that down. All right. Now what we're going to do is we're going to calculate A, B, and C for the first triangle. What is the first triangle? The first triangle is this triangle. What do you think the second triangle is? Yeah, it's this triangle right here. So I'm going to calculate the area of two triangles. All right? And then, when I get those, guess what I'll do? I'll add them together, and that'll give me the area of the quadrilateral. And then I'll move over to this guy. And I'll call this guy the first triangle, and then this guy the second triangle, or the third and fourth, if you want to call it that way. Then it'll be the first for each one of my four next nested loops. Okay? All right, so now what am I going to do? I'm going to calculate A, B, and C. Oh, well, what's A, B, and C? Well, I'll show you what A, B, and C is. What do you think A, B, and C are? Let's pick this quadrilateral right here, this triangle right here. What do you think A, B, and C are, if you had to guess? So, A, B, C. There you go. Simple enough, right? So how do I calculate A? Well, let's go back to this original one. Just undo all this. So if this is A, this is B, this is C. We're in three dimensions, though. So how do I calculate A? Well, this is my X coordinate, this is my Y coordinate, and this is my Z coordinate. So the way I'm going to calculate A is it's going to be the difference of my X's minus the difference of my Z's, because I don't have any Y coordinates, right? So let's go and look at this. It's going to be the difference of my X's versus squared plus the difference of my Z's squared. So I just plug it through the distance formula. That makes sense? Calculate B. It's going to be my Y's and my Z's, because now I'm only moving in my Y direction and in my Z direction, even though we're calculating 2 points in 3 dimensions. All right, now for C, guess what I have to do? I have to use all 3. Why do I have to use all 3? Because this has, we'll say, an x0 coordinate, a y0 coordinate, and a z0 coordinate. And this coordinate has a, I'll say, an x1, a y1, and a z1 coordinate. So I actually have to calculate the distance using the 3D distance formula, which you've probably all seen at some point in your life. And so that's why the C value, I have to use all 3 coordinates, whereas the A and B I only have to use 2 coordinates. Even though technically I could still plug in 3 coordinates, it would just be 0. Okay? Because either your X value doesn't change or your Y value doesn't change. I shouldn't say 0. It is the same, so it's almost like it's 0. Is that clear? And then I just calculate, because I already know A, B, and C, I just calculate S. And then guess what I do? I say I'm going to call this surface area 1, and I plug into Heron's formula. And I don't have to even understand how it works, because somebody figured it out at CE60. Okay? And we've accepted it. So I've actually seen the proof of it. I couldn't prove it, but I can look it up. All right, so now what I'm going to do is I'm going to go in here and I'm going to do the exact same thing for the upper triangle. All right? All right, so let's think about that. All right, so my A now, okay, so my A, well, let's go look. So now we're going to say this is the A value, this is the B value, and the C value will be the same. So all I really do now is just reverse them. Before I was taking the difference of the X's for A, now I'm taking the difference of the Y's. Now I'm taking the difference of the X's, but look what happens. This guy right here is the exact same as this guy, because it's the exact same hypotenuse. Calculate my semi-perimeter, calculate a surface area 2, and then I say my total surface area is equal to my surface area, which I initialized at 0, plus surface area 1 and 2. And then I cycle until done. So it's just like volume, except now I'm having to calculate the area of 2 triangles, add them up, and iterate. So was that really all that bad? Nifty, isn't it?
It is.
But it's easy. If it's not easy, what's hard about it?
Doing it without the hero.
Yeah, I don't know how you do
Okay. That would be hard.
that. Yeah, you could actually do it, but what you would have to end up doing is, like, if you didn't know that formula, you would have to go in and calculate like angles, and then figure out your base and your height, and you could do that. But Huron's formula just makes it a snap. All right, sounds great in theory, but let's see how it actually works. All right, so let me move this guy over here. I've got a couple answers that I've already calculated. So let's run it, and let's say my lower bound is -2, my upper bound is 2, -2, 2, and then number of divisions. Let's put in a I don't know. Let's put in 10 and see what happens. Well, what do I get? I get 52.028. What's the actual answer? 52.02. So that's pretty close, right? Does that make sense? So now do you see why I say numerical analysis is actually much easier than calculus? Because you literally, you could teach someone that just knew geometry. So go back to ninth or 10th grade in high school, and you could teach them the fundamentals of calculus. If they just knew geometry and you taught them a little bit of coding, just basically fundamentals like what a variable is, how to get message boxes to come up, and that defines a certain variable, and a for next loop, and then how to display a variable, export it or print it or display it or something like that. You could have, I think, easily 10th graders doing calculus 1, 2, and this is really getting into calculus 3 when you start calculating volumes and surface areas. Do you disagree with that statement? No?
And that's what we're really talking about is volume stuff.
Exactly. But do you see how easy it is using numerical analysis? It's like, man, this is a breeze. And at the end of the day, as an engineer, more often than not, you're looking for a number. And so this actually just gets straight to the heart of the matter and says, well, I'll just give you a number instead of some complicated formula. And then you have to plug in the limits into that formula. Because if you think about it, even if we could get this in closed form solution, we're not done. You have to then get it in closed form solution, plug in -2, +2, -2, +2, get 4 points, subtract them out. Okay, so let me plug in, say, a -2, +2, a -2, a +2, and then let's plug in 100 and see what it gives. Okay, so if we plug in 100, we get 52 point, basically 09.01, so it's getting closer. All right. Okay. Is that good? Everybody got it? Because we're pretty much done now with calculus. All right.
I guess we're agreed.
Yeah, I mean, what else is left to do? I mean, seriously, like, I guess I could do something with triple integrals, but like I said, that's kind of bean counting sort of thing. I want to show you something I think is kind of neat, and I'm going to give you guys a homework like that, like this. Okay, so let's suppose I have this function, y is equal to x squared. And this is from just integrating and calculating areas and arc lengths. Okay, so this is my function. Here are my limits. So with the function that I gave you from the book that I wrote, that's why I call this, not that I wrote, that I referenced below and then I modified, we can calculate the area using this integrate function, right? So we integrate C4, which is the actual function itself, the reference variable with respect to B, so this cell, this variable here, from the limits 0 to 1. So everyone understand what this guy right here is doing? It's just integrating that function. All right. And then I created one called arc length, and it's just calculating the arc length. All right. So what I want to do is I want to ask a question like, if I set this lower limit equal to 0 and change this limit, are there values such that the area is equal to the arc length? Hmm.
So, goals, that's all.
Yeah, we'll go see. Yeah. So we know the answer is yes, and the answer, one of the answers is 0. So I'm just going to type in 0.00001 because if I plug in 0, it gives you an error. So we know that 0 is an answer. Agreed? So what's another answer? I don't know. I don't know. Maybe 5? No, 5. How about 2? Not 2. Okay. Well, I don't know. Let's change to numerical analysis technique, goal seek, or Newton's method, and do a what if analysis. And so I'm going to say, all right, I want to set the difference of these two equal to 0 by changing this upper bound. Oh, it goes to 0. So that is one of the convergence points. Okay, well, what's another convergence point? Oops, wrong one. I don't know, let's make a guess of like 3. Let's see if that works. So set this difference equal to 0 by changing this cell.
So just like Newton's method,
Yeah.
where it starts.
Yeah.
It depends on where you're going to get that relative.
It is, exactly.
Okay.
So we can see that actually 3.22 is an answer. So do you know how hard this problem would be if you were going to try to solve it by hand? Well, one, you couldn't get the answer because I don't know if you can integrate that with +1 or not. But anyway, it would actually be hard because think about it. You're solving for the value of the limit in two integral equations. All right, and then what happens if one of them happens? You can't solve in closed form. You're dead in the water. So that is really just in a problem that took me mere seconds. You know, if I just gave you that problem, just cold, out of the blue, before you let's suppose I gave you that problem um, in January. Think about how many days you would probably work on that problem.
Still be on
You'd probably still be on it. No, I don't know. I mean, I'm serious. Just a simple problem like, oh, I want the area of this function from 0 to some value to be equal to the arc length of that same function from 0 to some value. You tell me that's some value. What? Okay. So I'm going to actually show you what the graph looks like, just so we kind of. So I'm going to start off, like I say, at point 1, and I'm going to copy this, paste it here, and then I'm going to change this to like point 2, and then I'm just going to drag down to like, I don't know, just drag down to 100 or something. I probably didn't need to go that far. Ooh, that didn't work. No, it did. Oh, there we go. I knew there was a problem. I knew that something was going on. So I'm just going to Shift Control C. I don't want to really go that far down. Let me go to like 5. There we go. Okay. I'll just paste this, and then I'll go down here to Control C. And then I'll do insert graph, and then I'll do something like that. Okay, so that is what the graph actually looks like. So we see that over here, 0 is an answer. And then it kind of comes down, and it goes back up, and then it crosses, and then it appears to go up. Now, you could even go to the next level and say, well, I want to know the minimum value of this. Well, it looks like it's occurring at 2, -2. So this may be one of those that's that you could actually tease out. But if you had like, say, e to the x plus the natural log of y or something, then it probably, or yeah, something like that, e to the x times x to the x or something, who knows. Then it probably is going to be some complex function. But then you could even go in and take the derivative of this difference. So, and that's the great thing about numerical analysis, that if this is the response using numerical analysis, you can go in and actually take the derivative of your responses. So that would really be a hard problem if you think about it. So I want to know the point such that the difference between the area and the arc length is minimized. You know, like I don't even know what to say about that. That's like a foreign language. I mean, think about it. If someone actually gave you that problem, let's see, there we go. Basically, I ask you to find this point. um, but do you see how to get this point even, which is about 3.3 or something, that this actually, it took quite a bit of computation for me to go through and to calculate each one of them, okay? Or I could just plot the results like I did, or I could use Newton's method, and it figured it out pretty quickly. So let's do that one more time and just watch it.
You said if we had numerical analysis, back then we didn't have symbolic.
We would, because it's something that human beings would have developed.
That's,
Am I wrong? Did I do something wrong?
and you're one up from,
Uh,
right?
H, E, no, I'm good.
Okay.
Yeah, I think. I don't know. Oh, I think I made a mistake. You're right. You're right. You're right. No, I'm not saying you wouldn't. We would have always developed symbolic. I'm just saying a lot of people wouldn't have been quite impressed. 3.22. But you have to realize the symbolic notation was developed because you were trying to reduce. I mean, back in the day, you could have gone through and brute forced this, calculated each rectangle or each half cube or whatever. It would have just taken you forever. So calculus was developed so you could get a closed form solution and then just plug in your limits and get an answer. Okay. All right, so you guys get it? Because on the next homework, I'm probably going to give you a problem very similar to this, except it's probably going to involve volumes and surface areas. Mm, yeah. All right. Well, that's all I have for today. Any questions?
So do you want to all code
No.
or just go see stuff?
Goal seek stuff. Goal seek stuff and using these functions that we have worked together to develop. So enjoy the fruits of your labor. And ultimately, well, this is actually useful because if you want to do work in Excel, having these functions that calculate integrals and double integrals and surface areas and arc lengths are useful. Um, but a lot of times you may just use like Mathematica or MATLAB or something like that. But if you ask Mathematica one of these questions, it's going to grind for a while because it's going to be a little confused, especially if you don't say like NSOLV or something like that. Um, But that's a good thing about Excel, where it's relatively dumb. It's like as long as you put in what you're looking for, it'll just grind on it and give you the answer. Mathematica tries to figure out exactly, in a more sophisticated way, what the answer should be. It's like, no, I'm just looking for a number. Okay?
I know on the donut company, and they won't.
Uh-huh.
I had a non-linear, so a simplex, and it was taking a while. It was like
Yeah,
sub
just
problem 128, sub problem, or sub routine 18,
right, right.
stuff like that.
And then as soon as you plugged in simplex, what happened?
It was,
So now do you know why you would use the simplex?
yeah.
Yeah. That's why it's it's convenient if you can actually linearize your problem. Okay?